Swayam Prabha. Digital India. Educated India.
Hello my dear students, welcome to learner will be able to understand IUPAC nomenclature of some of an examples of an polynuclear aromatic hydrocarbon. So in this session we will be seeing only 3 polynuclear aromatic hydrocarbons, and in the remaining session or in the next lecture we will see 2 more polynuclear aromatic hydrocarbons and some relevant derivatives of this IUPAC nomenclature. Learner will be able to understand the synthesis and reactions of polynuclear aromatic hydrocarbon. Learner will be able to understand uses of polynuclear aromatic hydrocarbons. So for what purpose they are being utilized on the commercial scale, and that is the need to study this polynuclear aromatic hydrocarbons. So the contents for this session: firstly, introduction to polynuclear aromatic hydrocarbon, and also the classification of this polynuclear aromatic hydrocarbons and why they are said to be polynuclear, and what is the role of an aromatic ring in it. After that we will see nomenclature of naphthalene or diphenylmethane and triphenylmethane. So there are almost 5 polynuclear aromatic hydrocarbon in the syllabus, and from this we are conducting 3 examples in this session. After that we will see synthesis method of naphthalene, diphenylmethane and triphenylmethane, and there are some reactions of naphthalene, diphenylmethane and triphenylmethane. In between that we will also see reactivity of an naphthalene. So Why that only alpha product it has been forming rather than beta, or why it is predominant. Also we will see the reactivity and some resonating structures of an naphthalene. And lastly we will see uses of naphthalene, diphenylmethane and triphenylmethane. Most of they are utilized for dye purposes, and we will see individually, and all these contents we will see individually for individual classes. So let's first see what is polynuclear hydrocarbons. Hydrocarbons are made up of two or more benzene rings. So here it deals actually with an aromatic polynuclear aromatic hydrocarbons. So when it comes to only an polynuclear hydrocarbons, so it may be not an it is not having an aromatic ring, but we are dealing with a chapter or a module that is related with an polynuclear aromatic hydrocarbons. So the hydrocarbons are made up of two or more benzene rings fused together, or isolated benzene rings, or non-benzenide nucleus are called polynuclear hydrocarbons. Not just only polynuclear hydrocarbons, but polynuclear aromatic hydrocarbons. Though it is not having an benzene structure, but there are some rings which do have an aromatic structures. So we will see some of an representative examples from this polynuclear aromatic hydrocarbons. So one of them, that is naphthalene. Two benzene rings, they have been fused. After that we will look phenanthrene. So phenanthrene and anthracene, they are having an aromatic ring, number of aromatic ring 3. But only the difference between this phenanthrene and anthracene is that the anthracene, it is having a linear chain of an aromatic ring, or linearly they are been arranged, and phenanthrene, it is not it is not a linear one, or we can say it is a non-linear one. After that, diphenylmethane. So name itself indicate having two phenyl rings, and methane is a adjoining moiety between two phenyl rings. After that, trimethylphenane, similarly as dimethylphenane, it is having an 3 phenyl, so triphenyl, and in between having an methane. So this methane, it is connected with this phenyl, and so it is said triphenylmethane. So these 5 structures, or these 5 compounds, we will be seeing in this polynuclear aromatic hydrocarbons as an representative examples. Now we'll see the classification of an polynuclear hydrocarbons. So first one is benzonoid, and distinguishing to it, it is non-benzonoid. So benzonoid, name itself, it is indicating that it might be having an benzene aromatic ring, and non-benzonoid, it is not having an benzene structure. Though it is not having an benzene structure, but it is aromatic, because all the carbons, they are been sp2 hybridized, they are planar, and number of an pi electrons, it is 10 in case of an azulene, so it is an aromatic structure. After that, benzonoid, it has been classified into 2 parts, that is isolated and fused ring. So isolated means benzene ring, it has been separated by some means or by some bonds, or having some moieties in between, like we have seen the structure of an trimethylphenane and dimethylphenane. So this one, it is the structure of an biphenyls fused. Again, there are 2 categories in case of infuse. So one is linear and second one is angular. So naphthalene, it is a linear structure, as it is a straight. That is alpha and beta substituted. So numbering starts from an alpha position. So as it has been said over here, that from an alpha position, number 1 starts, 2, 3, 4, and this fused carbon, it is not given number because it does not have any kind of an substitution. So it has been neglected because there are all 4 bonds of an carbon which does not allows any type of an substitution, because there is no hydrogen over here, so it has been neglected. And after that 5, 6, 7, 8 respective. So this structure generally it is called alpha naphthol. As per IUPAC it is said to be an 1 naphthol, and OL, it is representing OH or alcohol at the end. And due to this alcohol substitution or OH substitution, it is indicating OL at the last. So general name alpha naphthol and IUPAC name, that is 1 naphthol. General name, that is beta naphthylamine, because amine it has been substituted at an beta position. As you can see, this is the second one is an beta position. So IUPAC, as per IUPAC, we will say it is an 2-naphthylamine. After that 1,8-dibromonaphthalene. So at first position and 8th position, as here you can see that first position and 8th position, it has been substituted by 2 bromine, so dibromonaphthalene. So now we will see some properties of a naphthalene. Naphthalene is colorless solid which forms shining flake crystals. It is very volatile and sublimes slowly at room temperature. Naphthalene gives aromatic electrophilic substitution reaction, as we will see in chemical reactions. The product of monosubstitution is either alpha or beta depending on the conditions. And in case of an alpha and beta substitution, as we have seen, there is only 2 types of substitution, most often alpha and beta, but alpha always predominates. And why does it predominates? Only there is an alpha substitution most of the time and not beta, but for an harsh condition it may be an beta. So we will come across such type of a reaction, that is alpha as well as an beta. And also we will see why the reactivity at an alpha position it is more compared to a beta position. Now we will see synthesis of a naphthalene and why that alpha beta predominates. We will see uh, when we come across an chemical reactions of this naphthalene. So the first method of synthesis of a naphthalene, it is from coal tar. Naphthalene is most abundant single chemical compound present in coal tar, so it is almost 10%. The middle oil fraction, having an almost temperature 170 to 230 degrees Celsius of an coal tar, chilled, and after chilling it forms an naphthalene crystal. Synthesis of naphthalene from 4-phenyl 1-butene. 4-phenyl 1-butene is passed over a red hot calcium oxide to form naphthalene. So this is structure of an 4-phenyl 1-butene. As we can see, it is an phenyl ring and having 4 carbons, and these 4 carbons, it is the double bond, it is at the first position, so it is given over here 1, and phenyl ring, it is at an 4th position as per the butene numbering 1, 2, 3 and 4, so it is said to be an 4-phenyl 1-butene. So this 4-phenyl 1-butene water molecule, it is been removed and it forms an cycle, and this cyclization, it has been substituted by OH, and to reduce this OH or to remove this OH, it has been treated with an zinc, and as soon as it has been treated, it forms an naphthalene at the end, forming an zinc oxide. After that synthesis of an naphthalene, so one of an important method, that is Haworth synthesis. Benzene, it is treated with succinic anhydride in presence of an aluminium trichloride. So such kind of an reaction, it is carried at dry conditions. Usually the reactions, they are carried out in round bottom flask and condenser, but beyond that, it is having some special conditions whenever we are doing any such kind of a reaction with this Lewis acid, that is AlCl3, because it is highly water loving, and when it comes in a contact of a moisture, so it becomes an inactivated. So to remain water free or moisture free reaction condition, the condenser whatever we are using for in this reaction, so it has been either it is having an guard tube of an calcium chloride, or either it is having an argon type of an balloons, so that the moisture present in between, it has been sucked out or it has been purged out, and due to presence of such type of an gas or this calcium chloride has an ability to remove the moisture from a reaction, and that is why AlCl3, that is Lewis acid, it does not deactivate, but as soon as it comes in contact with water, it does deactivate. So for this type of a reaction, whenever there is an AlCl3, that is Lewis acid, so such type of reactions, they are carried always in dry conditions, so then only we can get a good yield. But if conditions are not maintained, so either there will be very less yield or there will be no reaction. It forms an intermediate, that is benzoyl propionic acid. After that, it has been reduced. So particularly reduction of such kind of a reduction, whenever we come across the such kind of a reduction, that is zinc amalgam, we can say. So zinc, it has been alloyed with an mercury, and in presence of an acidic conditions, it forms it only reduces and double bond, or we can say carbonyl type of a double bond, and it forms an gamma phenyl butyric acid. After that, for cyclization, hydrofluoric acid, it has been utilized, and similar type of a reaction that has been carried out to reduce this carbonyl. So this alpha tetralone, now it has been reduced. So particular this reduction with zinc amalgam in acidic condition, particularly it reduces only an carbonyl, and it forms an tetralene, and this tetralene, it has been heated in presence of an PD and carbon dioxide, and now it forms an naphthalene. So it is quite lengthy process, but it is one of an important synthesis method for an naphthalene. Before moving towards chemical reactions of a naphthalene, one should know why this alpha product predominates in naphthalene, and why not beta? So oftenly it has been seen that there are two types of an substitution, alpha or either beta, but alpha predominates. In electrophilic aromatic monosubstitution of a naphthalene, alpha product is formed in the preference to beta carbon. This is understood if we examine the intermediate carbonium ion. The two resonance structures can be written for the intermediate carbonium ion obtained from attack at alpha position without involving other ring, whereas only one structure is possible for substitution at beta carbon. If we see the structures of an alpha position of an alpha attack of an electrophile, so we can get two types of this resonating structures, but there is no involvement of an further ring. So just we have considered here only two structures of an first ring, or two carbocations of an first ring. So here you can see that it is forming and carbocation at carbocation of an two resonating structures, and as soon as the electrophile it comes, the pi bond breaks, and this pi bond it breaks and shift an electron towards an first carbon, and due to which second carbon it becomes an electron deficient, and now here you can see that second carbon it is an electron deficient, and after that the pi electrons are been shifted towards an second and third carbon, and now fourth carbon it becomes an electron deficient, as we have seen in case of an benzene also. So if you remember that shifting of an electrons, so it takes place for to resonate the structures and to make the structure stable. Now coming towards an beta position, if electrophile it attacks at a beta position, so there is only one type of an carbocation it has been formed. So there is no another carbocation formed, because here it cannot now shift towards another carbon, as we are not considering a second ring and just for the first ring. So there cannot be any more resonating structure, and that is why only alpha carbon or alpha products they are been formed and not an beta products. Beta products are formed but at an harsh conditions, but alpha it predominates because it is having two resonating structures. As the resonating structures increase, the stability of any molecule does increase, but beta it is not having any pi bond closer to it for an exchange, so this bond it does not break because it is intact with another fuse ring. If there is by an sequence it is having an pi bond, then only pi electrons will be shifted, but it does not happen, and due to which there is only one carbon which is having an carbocation, and that is why alpha predominates on beta because of resonating structures. Now we'll see reactions of a naphthalene. So first reaction, that is halogenation. Naphthalene reacts with chlorine and bromine in solution to form alpha bromo naphthalene. Second reaction, that is of a naphthalene, it is nitration. When warmed with mixture of concentrated nitric acid and sulfuric acid, naphthalene forms an alpha nitronaphthalene. Structure of a naphthalene, and it is warmed just at 50 degrees Celsius. So we require H2SO4 also, because without it nitronium ion it is not formed, and it gives an alpha nitronaphthalene. After that, next reaction, that is sulfonation. On treatment with concentrated sulfuric acid at 40 degrees Celsius, it yields alpha naphthalene sulfonic acid, and at 165 degrees Celsius it yields beta naphthalene sulfonic acid. The structure of a naphthalene, just it is warmed at 40 degrees Celsius, it forms an alpha naphthalene sulfonic acid, and when it is having a more harsh condition, such as we have discussed earlier also, why only alpha product predominates and why not beta, it is also giving a beta product, but the conditions are some harsh, and so now it forms an beta naphthalene sulfonic acid. So from this reaction you can understand that there is not only an alpha type of an product that we obtain, we also obtain a beta type of an product, but the temperature difference, they are quite, means we can conclude from it that when the reaction conditions are normal, at that time alpha product it has been formed, and when the reaction conditions they are beyond the normal, in that case we get a beta product. So 1,4-dihydronaphthalene, it is because at first position, so as we have seen in case of an IUPAC nomenclature, first position and fourth position. So at first position, it is now having, it has been reduced, and now it is having an 2 hydrogens, as this bond has been reduced, or these pi electrons are being converted to now a sigma bond, and the hydrogen, it has been replaced at 1 and 4th position. So that is why it is dihydro. Naphthalene is used as moth repellent to protect woolen goods also. Naphthalene is used for commercial production of phthalic anhydride. Naphthalene is used for making of an alpha naphthol, that is insecticide, and beta naphthol, that is tanning agent. Naphthalene is used for manufacturing of dyes, explosives, and synthetic resins. So dyes, it is one of an important use of an naphthalene. So some of an naphthalene derivatives, they are dyes. Naphthalene is used for manufacturing of drugs such as propranolol. It is anti-hypertensive. After that, antifungal drug, that is tolnaphthate, and after that nefazolin. So these are some of drugs which are having basic ring of an naphthalene as well. They are not directly nowadays not directly naphthalene it has been used, but naphthalene, it is a basic moiety in it, and from that basic moiety the reagents for a starting material for such kind of drugs they have been prepared. Now we'll see IUPAC nomenclature of two more molecules from this class, that is polyaromatic hydrocarbons. So one is diphenylmethane and second one is triphenylmethane. So for an IUPAC numbering, so first ring, that is first phenyl ring, so it has been numbered, and second ring it has been numbered with a dash. So it is for an indication, so on which ring substitution has been taken place, and this methane in between, so it is numbered as in 7. One of an type of an rearrangement reaction, that is Wolff-Kishner reduction. So benzophenone, it has been reduced with the help of an Wolff-Kishner type of an reduction reaction by using zinc amalgam, which gives diphenylmethane. And also we have seen earlier that what is this zinc amalgam, it reduces particularly an ketonic functional group. Reactions of diphenylmethane. So now we will see nitration, as we have seen the nitration in earlier some chemical reactions, that it requires an nitric acid as well as an sulfuric acid to form an nitronium ion. So diphenylmethane, when treated with and nitric acid and sulfuric acid, it gives 1 benzyl 4 nitrobenzene. The structure of an diphenylmethane and nitrating mixture, that is nitric acid and H2SO4, generating a nitronium ion. And so such kind of an electrophilic aromatic monosubstitution type of a reaction we are going through. So it forms an nitro product at 4th position. So the potassium salt of this diphenylmethane, it is used as an initiator for an polymerization. Diphenylmethane derivatives are a group of drugs used in treatment of variety of emotional and mental disorder characterized by tension, anxiety, and agitation. So there are lot many drugs in case of an CNS. So they are having a basic ring of an diphenylmethane, and also in case of an ANS, we can see such kind of an structures having a basic ring of an diphenylmethane. Now we'll see reactions of an triphenylmethane. So first one, that is halogenation. Bromine reacts with triphenylmethane, gives triphenylmethyl bromide. So it is one of a simple reaction, just replacing and concept of an polynuclear aromatic hydrocarbons. We have seen the classification, and there are two main classes, benzonide and non-benzonide. alpha, it requires a minimum conditions, or easily we can get a product of an alpha, but for an beta it requires an harsh conditions. After that, Friedel-Crafts alkylation we have seen. Friedel-Crafts alkylation also gives a different type of an product, that is alpha and beta. So here the solvent plays an important role. After that, reduction with the sodium and ethanol. So it forms 1,4-dihydronaphthalene. So from overall we can understand that beta alpha product, they are readily being formed, but for an beta product we require some drastic conditions of an chemical reaction, so that we can also get a beta product. So more oftenly we just get alpha, and after that we get an beta. So beyond that we does not get any type of a substitution of a product. And lastly we have seen oxidation. So carbon number first and carbon number fourth, it has been oxidized. After that we have seen the reactions of diphenylmethane. So it is nothing but Friedel-Crafts type of an reaction, that is benzyl chloride react with an benzene in presence of an Lewis acid. After that, reduction of an benzophenol by zinc amalgam. After that, toluene. So from toluene it is again a multi-step type of an reaction, just we have mentioned over here a starting material. After that, now reactions of an diphenylmethane. After halogenation it forms an chloro derivative. After nitration it forms a nitro derivative. Nitro derivative, it is at a fourth position only. After that, cyclization, so it gives a cyclic product, and after that oxidation it gives an benzophenol. So here we have also seen by reduction of an benzophenol we does get an diphenylmethane, and from oxidation of an diphenylmethane again we can get a same product, that is benzophenol. Triphenylmethane. So benzene, 3 moles of an benzene, it is reacted with chloroform. So it is type of an Friedel-Crafts type of an reaction. Halogenation, reaction of an triphenylmethane gives an halogenated